So we're going to start chapter 2 with the trigonometric functions of acute angles. So we'll start with acute, we'll get into any, and then we'll get into applications of trig for acute and obtuse angles. So let's just go over the right triangle-based definitions of the trig functions. When we learned this a little bit ago, we used x, y, and r to define sine, cosine, tangent, and their reciprocals. But now we can put this onto a right triangle where the opposite side from our angle theta is now going to be called the opposite from angle A. Oh my gosh, I cannot spell the word opposite today. Let me try that 1,000 times again. Opposite. And the value of x, the horizontal displacement, is the side that is adjacent to the angle A. So now we're talking about our angle theta in terms of capital letter A. So when we're working with triangles, you will see angles represented as capital letters or Greek letters. Side lengths are going to be represented by lowercase letters, and that's going to be sturdy throughout the whole course. If it's an angle, we're using an uppercase letter or a Greek letter, theta, omega, all that stuff. Side lengths are lowercase letters. But we're going to call these now the opposites and the adjacent. If you think back to geometry class, what is this side length called? The hypotenuse. So now we're going to redefine all of our trig functions from x, y's, and r's to the sides of a right triangle. So sine will now be, instead of just y over r, it will be the opposite over now what is called the hypotenuse. I'm going to go straight down. Cosine is the adjacent side, x, over that hypotenuse, r. Tangent is y over x, so it's going to be the opposite over the adjacent. Do these words sound familiar to you? Great. Here's how we probably taught you back in geometry class. Do y'all remember the acronym? SOHCAHTOA. If you're trying to find sine, it is the opposite over the hypotenuse. So if you're finding cosine, it is the adjacent over the hypotenuse. And if you're finding tangent, it is the opposite over the adjacent. SOHCAHTOA. That is like geometry basics for trigonometry in pretty much every class. That acronym has probably been used since the beginning of time. I don't even know where it came from. I just know I learned it. SOHCAHTOA. Now great, those are the three main trig functions. We've already introduced the reciprocal trig functions, cosecant, secant, and cotangent. So if we wanted to redefine those in sides of a triangle, you just flip the fraction. So instead of opposite over hypotenuse, that means that cosecant is going to be the hypotenuse over the opposite. Secant is going to be the hypotenuse over the adjacent. And cotangent is going to be the adjacent over the opposite. Again, I'm just flipping those fractions the same way we flipped them when we were using x, y, and r to define our trig functions. Now we're going to put them in right triangles, so we look at right triangle trigonometry. We ready to see what this looks like? Cool. In that we are now using triangles, we aren't necessarily using an angle in standard position. So it is very important you make sure you know which angle we are talking about. This question in particular wants you to find the sine, cosine, and tangent for angles A and B. So I'm not going to use a color coding here because we're switching angles. So if I were to color code them, you'd get confused. If we were doing the sine of angle A, that means I'm looking at angle A and I'm trying to see what is opposite from angle A. So what is opposite of angle A? 7. Then what is the hypotenuse of this triangle? So the sine of angle A is 25. What? 7 over 25. If I was going to do the cosine of A, I want the side length that is adjacent or touching angle A, which is 24. And then I want the hypotenuse, which is 25. If I go to do the tangent of A, we want the side that is opposite of A, which is 7, over the adjacent, which is 24. So this one would be 7 over 24. Make sense? Great. Here's the reason why I didn't happen to color code this particular problem. In reality, you'd be able to color code all these things with the colors I've been using all the time. But now, the second part of this problem is not asking for the reciprocal values. It's telling me to switch angles. Now I'm going to do the sine of B, which means now I'm looking at this other angle B, big B. What is the opposite of big B? Opposite, the side opposite of big B. 24. What is still the hypotenuse, though? 25. If you accidentally were still looking at angle A, you'd be giving me the wrong ratio. We have to make sure we're looking at the correct angle when we're doing right triangle trigonometry, because I could pick either one. Which means now if I'm doing the cosine of B, I want the angle that's adjacent to B over the hypotenuse. So this one will be 7 over 25. And then if I do the tangent of angle B, I'm wanting the opposite over the adjacent, which we've already identified would be 24 and 7. So that's 24 and 7. So make sure you know what angle we're talking about in our triangle because we're using both, potentially. But before we flip the page, is there something you notice about these numbers that we have for our sine, cosine, and tangent? Remember, we're looking at B. If we're looking at B, the opposite is 24. And the adjacent is 7. Thank you for making that question, because that is why we have to make sure we're looking at the correct angle. Let me go back to my question I asked out loud. Do you notice anything in particular about these numbers, these ratios, for angle A and angle B? They're like swapped, right? The sine of angle A becomes the cosine of angle B, and the sine of angle B becomes the cosine of angle A. What do you notice about the difference here? They're like flipped. There's a very interesting relationship between these trig functions when we're looking especially at a right triangle, because the only degrees we have left to play with since we have a right angle is 90 degrees, which means these functions are actually titled cofunctions, which is different than reciprocal functions and will be different than inverse functions when we get there. So this is particularly a property of these functions called cofunctions. If we're talking about cofunctions, we're talking about the functions whose, with different angles, end up with the same trig ratio. So this is what you guys noticed on the front. You noticed that sine of A and cosine of B was the same ratio. Tangent of A and eventually cotangent of B were the same ratio. And if I extend it a little further, secant of A and cosecant of B, because those are the reciprocals of sine and cosine anyways, are going to be the same. So these functions, sine, cosine, tangent, cotangent, and secant, cosecant are cofunction pairs. So now we're pairing them up in different ways, which I know can be confusing. We're not talking about their reciprocals, we're talking about their cofunctions. The relationship between cofunctions is right here, that they are a 90-degree difference from each other since they will have that relationship of the ratio being the same. And this comes from the fact that it is a right triangle. Okay, so I have listed in this main idea bucket right here the cofunction pairs so that you know which ones go together. And then the relationships defined by each and every single one. So sine of A is equal to the cosine of 90 minus A, since that would be angle B in a right triangle. And you can read all of the rest of them. These relationships, these formulas, will allow us to evaluate functions in a right triangle very easily. And here's why. If I wanted to know the cosine of 52 degrees, and let's say for some reason I had a chart of the sines of a bunch of angles, what I could do is instead of writing cosine of 52 degrees, I could write it in terms of its cofunction. Cosine goes with sine, but only if we take 90 degrees and we subtract angle A. So the angle from the cosine function. Y'all see how I just bloop bloop dropped it in there? Mm-hmm. So what is 90 minus 52? 38 degrees. So cosine of 52 degrees will be the exact same as sine of 38 degrees because these are a cofunction pair. Let's do the same thing for tangent. If I want to write tangent in terms of its cofunction, what is the cofunction with tangent? Cotangent. Ooh, don't say cot. Yuck. Cotangent. This is going to be 90 minus the angle I was given in the tangent function. What is 90 minus 71? 19. So tangent of 71 is the same as the cotangent of 19 degrees. And again, this is because these are cofunction pairs. And in a right triangle, they will end up having the same ratio. Last one, let's see if we can get this done before that lunch bell. Ooh, probably not going to happen. It's like got 5 seconds left. Okay, after lunch, we'll pick it up right here. So right before lunch, we were on part C, and we're doing cofunctions. So they are all in pairs. What is the cofunction with secant? Cosecant. So they differ by 90 degrees when their ratios are the same. So the secant of 24 degrees can be written as the cosecant of 90 minus 24 degrees. And what is 90 minus 24? 66 degrees. So these are cofunctions. If it asks you to write a function in terms of its cofunction, this is what we're talking about. So there's many different ways we can change or rewrite trig functions. We're going to have to start keeping track of which one I'm asking for. This one is a cofunction. Since these are cofunctions, we can take the cofunctions in equations and equate their arguments with each other. What I mean by that is it says find one solution for each equation. Assume all angles involved are acute angles. But we have the cosine of theta plus 4 degrees equal to sine of 3 theta plus 2 degrees. Cosine and sine are cofunctions, and if they're equal to each other, that means their angles have to add up to 90 degrees because they're the same in the triangles, and the only angles we have left are 90 degrees to work with. So what we're going to do is we're going to take the argument of the cosine function for theta plus 4 degrees, and we're going to add 3 theta plus 2 degrees, which is the argument from the sine. These should add up to equal 90 degrees. So we can solve for theta. Theta is like a missing variable, like an X. It's just a Greek letter instead of a, what are those letters called? Roman letters?
Roman numerals?
No, not Roman numerals. What is the name of the alphabet we use?
A, B, C, D?
Yes, that one. What is that called? I'm so blanking. Well, yes, it's a type of alphabet. It doesn't matter. I'll think about it and I'll get back to you later when it's like it'll come back later. So if we combine our like terms, we actually have 4 thetas floating around on this side and 6 degrees. So we can solve for theta by subtracting 6 degrees to the other side. That gets me 84 degrees. Then divide by 4 on both sides. 84 divided by 4 is 21. So our theta, our missing angle, is 21 degrees. So we can add the arguments together. If they're cofunctions, they should equal 90 degrees. So in part B, we recognize that tangent and cotangent are cofunctions. So all I have to do is take their insides, 2 theta minus 18 degrees, and add theta plus 18 degrees, and they should be equal to 90 degrees. Let's work smarter, not harder. What is negative 18 plus 18? 0. It's like they cancel each other out, which means we end up with 3 theta equal to 90 degrees, which means theta is how many degrees? 30 degrees. Let's discuss how function values change as we increase our angles. So if you see in the picture, oh no, thank you, I didn't hear it. We have these 3 triangles representing a small angle, a medium angle, and a big angle. See how the angle gets bigger for A each time? No. Let's track what's happening to the side lengths. On this one, let's track Y. Okay. As we make the angle bigger, what's happening to Y? It gets bigger. As we make the angle bigger, what's happening to X? It gets smaller. So to keep this an actual right triangle, we have this relationship between the x's and y's, which then means we have a relationship between sine, cosine, and tangent as angles change. As A increases from 0 to 90 degrees, the sine of A is also going to increase because the y value, which is part of sine, y over r, is increasing. So if our numerator is increasing, our fraction is increasing. Cosine, since the x is getting smaller, cosine of a is going to decrease because the x, or the numerator, is getting smaller. We're making a smaller ratio. Tangent is y over x, so we have a numerator getting bigger and a denominator getting smaller, which means that the number is going to increase. Okay, let's think about this now for our reciprocal functions. We're still looking at angle A, but now we have it flipped over. Cosecant is y, just kidding, it is r over y, which means my denominator is getting bigger. What happens to a number when the denominator gets bigger? The number gets?
Wait, is the denominator on top or bottom?
Denominator's bottom.
Oh, it decreases.
It's getting smaller, so it's decreasing. So secant is r over x, which means now the denominator is getting smaller, which means my actual fraction is getting bigger. Cotangent is x over y, so we have a numerator that's getting smaller and a denominator that's getting bigger. What's happening to the number? Decreases. So we have these different trends among our trig ratios for what's happening as we increase the value. So what that means for us is we can answer questions like example 4. It says to determine whether each statement is true or false. Is the sine of 21 degrees bigger than the sine of 18 degrees? Let's think about it. Is sine increasing or decreasing as we go from 0 to 90? Increasing. So that means sine of a bigger angle will be bigger than sine of a smaller angle. So this is a true statement because sine of 21 degrees will be bigger than sine of 18 degrees. The angle got bigger and sine gets bigger. So this is going to be bigger than this one, which is what this sentence is saying. For the second one, we're talking about secant, so we're looking here. Is the secant of 56 degrees less than or equal to secant of 49 degrees?
That's false.
That's false. 56 is bigger than 49, and if secant should be increasing as our value increases, that means a bigger secant is not going to be smaller than a smaller angle for secant. So this is a false statement. Now what's going to happen is we're going to start working with some special right triangles. And I know we don't necessarily maybe remember the relationships of these special right triangles because we've all told me that geometry was not maybe our best. But let's say we have this 30, 60, 90 triangle. In geometry class, you learned that there is a relationship, a special relationship between the side lengths of a special right triangle. This would have been x, x square root of 3, and 2x. So if we let across from 30 be 1, that means that the side length across from 60 is square root of 3, and the side length across from the 90 degrees is 2. This is the relationship of a 30, 60, 90 triangle. 1 square root of 3, 2. If you don't know this, look at your geometry notes. It's not the important part of today. What we're going to do is find the values of these 6 trig functions for this 60-degree angle. If we go to do this, we're going to do the sine of 60 degrees. Now, based on this triangle, it is the opposite over the hypotenuse. What is opposite of 60 degrees? Square root 3. Yeah, radical 3. What is the hypotenuse? 2. We can actually color code this one because for this particular question, we're only talking about 60 degrees. So we have our opposite, we have our adjacent, we have our hypotenuse. Okay, if we go to do the cosine of 60 degrees, cosine is the adjacent over the hypotenuse. What is adjacent to 60 degrees? 1. What is the hypotenuse? 2. If we go to do the tangent of 60 degrees, tangent of 60 degrees is opposite over adjacent. What is opposite of 60? And what is adjacent? So square root of 3 over 1 is just square root of 3. Yes?
So we don't need this increases, decreases for this part. We just go back to the one beforehand?
Correct. Yeah, this is like technically a different topic title right here.
Is that green?
Yeah.
No, it's purple.
Oh, I think.
Okay. So if we go to do the reciprocals, what's the reciprocal of sine? Cosecant. So if we're doing the cosecant of 60 degrees, we can do this in two ways. Number one, you can just flip that fraction or start thinking about the definition of cosecant. It will be the, I almost said radius, hypotenuse over the y, which means this will be 2 over square root 3. Can you leave that answer looking like that?
No.
No. How do we write this instead?
2 square root of 3 and 3 on the bottom.
Very good, over 3. If we go to the secant of 60 degrees, again, I could just flip that fraction or think about the definition. Secant is hypotenuse over x. What is the hypotenuse here? 2 over 1, which just gives me 2. If I go to do the cotangent of 60 degrees, again, I start to do the reciprocal of that, but let's go ahead and use the definition. The definition is adjacent over opposite. What is adjacent? Well, radical 3 on the bottom, no? Can we leave our answer like that? No, this becomes square root of 3 over 3. Now, some of you who took AP Pre-Cal last year probably start to recognize some of these values, yes?
No.
These are the things I forced you to memorize for our AP test. We will get there eventually with this class. But let's go ahead and write down the values of these special right triangles for all 6 trig functions. We already have the bottom row because the bottom row is a 60 degrees. So let's go ahead and fill that out. This is square root of 3 over 2, 1/2, and then square root 3. Cotangent was, what order did I put this in? Cotangent is square root of 3 over 3. Secant is 2, and cosecant is 2 square root of 3 over 3. Now we need to do the same thing, thinking about a 30, 60, 90 triangle, but 30 is our reference angle. So now my color code might be off, but let's look at that triangle. Sine is opposite over hypotenuse. What is opposite of 30? 1. So this is 1 over 2. What is the cosine of 30? That's adjacent over hypotenuse. Yeah, radical 3 over 2. And the tangent would be the opposite over the adjacent. Yeah, 1 over radical 3, which we would reduce, yes, to square root of 3 over 3. Cotangent of 30 degrees is the adjacent over the hypotenuse. So that would be square root of 3 over 1. Secant of 30 degrees is the radius divided by, I just said radius, hypotenuse divided by the adjacent. So hypotenuse divided by the adjacent would be 2 over square root 3, but I can't do that. So I move the radical 3 to the top and jailbreak the 3. We're looking at 30. Cosecant of theta from 30 degrees is the hypotenuse divided by the opposite, 2. Now, a 45-degree angle, we don't have the triangle written here, but you probably have some space somewhere on this page. Let's draw a 45, 45, 90 triangle. I'm going to put mine over here. This is the other special right triangle from Algebra 2, geometry class. A 45, 45, 90 triangle has other special properties. The special properties are that the side lengths have to be the same. It didn't look like I drew mine the same, so let me put the little tick marks to show you they're the same. And if they're the same, then they have the ratio of 1 and 1, which means that the hypotenuse is square root of 2. That's the ratios of a 45, 45, 90 triangle from geometry class. Anybody who's still retaking their SAT, this would be something that you want to look at. They love asking questions about your 2 special right triangles. These patterns, 30, 60, 90, 45, 45, 90. Okay, same concept. We're going to look at one of the 45-degree angles. We'll pick the one, I like the one that's flat, just I don't know why, which means that this is the opposite, this is the adjacent, and this is the hypotenuse. My reference angle is the one that increases. Yes?
I might have zoned out. How do we get those numbers?
The ones on the triangle? These are things from geometry class. There's a special relationship between the angles. Normally you would write x square root of 2. That's the properties for special right triangles. But if I make x equal to 1, then it's 1 square root of 2. It's the ratio of the side lengths to each other. Okay, let's do sine of this 45 degrees. Sine is opposite over hypotenuse, which would be what divided by what? 1 over square root 2. Yuck, you can't do that. So instead, how do I write it?
Square root of 2 over 2.
Square root of 2 over 2. If I do the cosine of 45 degrees, that's adjacent over hypotenuse, which would be what over what?
1 over
Which I would write down as
2 square root of 2.
square root of 2 over 2. Tangent would be the opposite over the adjacent.
2 square root of 2.
Oh, what's opposite of 45? What's opposite of 45? What's adjacent to 45? What's 1 over 1? Boom. Now we go to do the reciprocals. The reciprocals are just the flipped fractions, but if we're doing the reciprocal of 45 degrees, so cotangent of 45 degrees would be adjacent over hypotenuse. 1. Secant would be hypotenuse divided by adjacent, which is just square root of 2. And then cosecant would be opposite, just kidding, it would be hypotenuse over opposite, which is just square root of 2. Now, these values are something that we should be able to just know, and eventually we'll learn a lot of things about why when we get into unit circles and radians. That's chapter 3. If you were in pre-cal last year, I taught you a table for these 9 values. It's just the flipped direction, which is why it doesn't look normal. Look at this. 1, 2, 3. 3, 2, 1. It's the same patterns we had last year in that class. I've just turned the table. Okay? If you don't know what I'm talking about, it's because you weren't in my pre-cal class last year. We will discuss later. But these values are not ones I want you to put in a calculator, because all except for the ones that are 1, 2, and 1/2 are going to give you ugly decimals because they're irrational numbers. Instead, I want actual values for these numbers. So we will need to know if it's square root 2 over 2, square root 3 over 2, or 2 square root 3 over 3. You get it. Okay.